Hello everyone, this is BronyCalc, and we are going to be doing ARML 2017 individual round, the final pair, problems 9 and 10, in 10 minutes or less, starting now. So, problem 9. We have a number written in this form, 67 times 9 factorial plus 27 times 8 factorial, and we want to find the median of the set of divisors. So, for a set of divisors, if we write in increasing order, obviously it's going to be the middle one if it's odd, and it's going to be the average of the middle ones if it's even. It's only odd if it's a perfect square, so let's hope it's a perfect square and go from there. Factoring this out, we get 67 times 9 plus 27 all times 8 factorial. Or, this is 3 times 9, so 70 times 9 times 8 factorial. Now let's try to figure out how many of each prime factor there are. So starting with 2, there's one factor of 2 here, and then there's 4 multiples of 2, so that's 4 powers of 2, 2 multiples of 4, so that's another 2, and 1 multiple of 8. So we've got 8 powers of 2. Then we see here we've got 2 powers of 3 because 9, and then 3 and 6 both divide 8 factorial, so we have 2 here. So we got 3 to the 4th, then 5, 1 here, and 1 5 here. So 5 squared. And then the final one, we have 1 multiple of 7 here, and 1 multiple of 7, 8 factorial, so 7 squared. So it is a perfect square. That's really nice for us. We can just find the square root. So we have 2 to the 4th, or 16, times 3 squared, 9 times 5 times 7, or 80 times 9 times 7, 720 times 7, you should recognize 6 factorial times 7 is 7 factorial, 7 factorial is 5040, which is indeed our answer. So, done with that in under 2 minutes. On to pretty much the hardest problem of the test, number 10. So we have a rhombus, ARML, has all its vertices on the graph y equals 4x minus fraction of x, and then we have and then we're given that the area of the rhombus is 8, and we want to find the least upper bound for the tangent of A. So, for this one, we need to know. First off, we need to know what does floor x minus fraction x look like. So basically, let's start with just any integer, 12. Obviously, its fractional part is 0. It's an integer, so it's going to be itself. It's its own floor function. Then we go to 12.1, let's say here, 12.1. Well, now the floor is 12 still, but the fractional part is 0.1, so we're at 11.9. And we can keep going down till we get here. At 13, we jump back up because fractional part is 0 again. So we've got this straight line, which when we went forward 0.1, we went down 0.1. So it has a slope of -1, and it repeats over and over and over. What are the bounds though? Well, we notice that 12 is 12, 13 is 13, that's true for any positive integer. So I can draw a line here, and this is going to be y is equal to x, which has a slope of 1. 1 and -1 are perpendicular to each other, negative reciprocals and all that. So we got that there. And then over here we got 13, 11, 14, 12. It's y equals x minus 2 at the bottom here. But very important, once again this is perpendicular, but most important part about this is this line isn't on the graph. It never touches. There are holes here, and you need to remember these holes later. We'll get back to them. So, now we need to start working with the rhombus and figure out how we're going to fit it in. I'm going to draw another line here. So, for this rhombus, we need to decide what property we're going to look at. Obviously, the basic definition of a rhombus is all 4 sides are equal, but that doesn't help. I don't want to measure the side lengths, because that involves coordinate bashing, and that's just going to take way too long. We already only have like 5 minutes left. We can use the fact that it's a parallelogram, but once again, that's vector bashing, also going to take forever. Here's a nice property. Perpendicular bisectors. The diagonals are perpendicular bisectors of each other. So, we can use that, we can find the diagonals and start looking from there. So, I say so a lot. Oh well. So, we take 2 points on here, and we try to figure out what we can do with that. If they're on different sides, then the perpendicular is going to get stuck on these lines, as you can see. If I draw it, boop, 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 like that, perpendicular is going to get stuck on y equals x and y equals x minus 2 pretty quick. But if I choose diagonals to be on here, we're never going to get stuck. And why is this important? This is important because we want to be able to get our angle as close. We're looking for the least upper bound tangent A. If you know the graph of tan A, we know that it goes to infinity at around 90 and then it comes back. 0, 180. We're dealing with somewhere between here because it's quadrilateral. So we want to get it as close to 90 while still being below 90 as possible. Now, for most of these, we're going to get stuck at some point and not really be able to put it on there. But if we put it on here and draw the perpendiculars like this, it's going to be parallel to these lines and we can actually go pretty far. So we just have to figure out where we can go. Well, to figure out where we can go, you may notice that it looks like a ladder a little, so we need to figure out how long these rungs are, how far apart they are. Well, I know that this is 12, 12, this is 11, 11, so they appear to go in steps of root 2 if we're using this as our perpendicular. So we have one diagonal is of the length n root 2. And as a matter of fact, since it's a perpendicular bisector, we need symmetry on both sides. So it's going to be 2n root 2. And then the other one's going to be something else. So we need a way to find it. We're given that the area of ARML, our rhombus by the way, is 8. And we know that the area of a rhombus is given by 1/2 PQ. So let's say this is P, is our longwise diagonal. And Q is going to be R1. We know that PQ is 16. So Q is 4 root 2 over n. So, now what do we do with this? Well, obviously one of these angles, one pair of angles is going to be obtuse all the time. One is going to be acute all the time. We don't really have squares here. So, let's take the acute one. That's going to be A. We want to get as close to 90 as possible. So, we want the long one because obviously if we try drawing it, one is obviously obtuse, one is obviously acute. We want the long one. We want this long one to be as small as possible, so that the short one is as big as possible, so that our tangent is as big as possible. To do that, to maximize Q, we know that it needs to be stuck on one rung of our ladder. The rungs are length just less than root 2 because of this hole. I told you, remember it. A lot of people got stuck on that. So we need it to be just under root 2, let's say 4 root 2 over 5. Because we need n to be an integer. And you can't see that, so I'm going to put that like this for now. And we are running out of time, so really quickly, n is 5, 10 root 2. So we have P is 10 root 2, Q is 4 root 2 over 5. If we take half and half, that gives us one triangle with A over 2. 2/5, 5. 2 over 25. We use double angle tangent formula. 2 times 2 over 25. Can you see this? Yes, you can. Over 1 minus 4 over 625. That gives us 621 over 625. and on top we have 4 over 25. 4 times 25, because this is 25 squared, so we cancel it 25, move it to the top, 100 over 621, and with less than 10 seconds left, we do get it right. Oh boy, that was a hard one. Anyways, I hope you enjoyed this little challenge. You can tell me in the comments if you want to see another year done, and just tell me which year you would like to see. And be sure to like, comment, subscribe, and I will see you all next time.